Hi everybody, my name's Nick and I'm here on the couch today to talk about the Meshtastic LoRa radio network and why you should consider deploying local large language models onto your mesh and using them with different systems and sensors that you might be deploying or wanting to deploy on your network. This is a project I originally did for DEFCON 33 for the AI Village, and I will be bringing it back this year for DEFCON 34. So if you like anything that I do in the video today and want to see it in person, feel free to come visit us in Vegas, August 6th through 9th, later this year. But with that said, let's get in. Before we go too deep though, it's probably important to explain what Meshtastic is and what makes it so unique that would justify why you would want to consider deploying an LLM onto it as opposed to just other conventional stuff. Meshtastic is what's called a headless self-organizing LoRa mesh network. What this means is, unlike your conventional Wi-Fi network, which talks in higher frequency bands, it talks right around like the sub-gigahertz, 1 gigahertz cutoff in most cases. This gives it much larger range, anywhere from 2 to 4 kilometers, depending on how you are on the ground, but also makes it very, very slow. You can't do images on Meshtastic, you can't do videos, and your packet size is limited to roughly 200 characters per message. But you do get this, what I consider a very fun feature, which is Meshtastic is a self-organizing headless mesh, which means unlike your home Wi-Fi network where you have a dedicated router that does all the routing and anyone who wants to use it has to connect to and exchange a username and password and all this other jazz with the router to get the right SSID and right encryption key and all this other jazz, you don't do that with Meshtastic. Two radios that are in range of each other, as long as they're in range of each other, can just talk. And they can talk to any device that's in range with any of the other radios. This makes a hopping pattern kind of formatting where as long as you're within so many hops of yourself, you can reach them and they can reach you. This does mean there's no guarantee that you'll be able to talk to a specific node at any one point in time, but it also means that as you move around with the node, you can basically go to any city, and as long as you're all talking on the same frequency, you can just talk to everyone there. No extra connections or handshaking needed. This gets very fun when you start talking about like traveling or hiking or wanting to deploy stuff in remote areas because anyone who's nearby can use it. One of the funnier examples I saw of this was I was in Colorado last year, and someone had actually hooked up their solar-powered toilet to Meshtastic, so it would send periodic static messages over there that like everyone can kind of laugh at and look and be fun. So like it's a really cool network if you're wanting to do stuff in remote areas without having to get like very expensive. For example, this is my personal travel radio. This is a Seed Studio T1000. It's like $40, 40 or $50, depending on tariffs. This is also a Seed Studio. This is a little USB guy. He's $10. Like these are very, very cheap for their range. Because the network is effectively made up of people who use it, you're not really paying constant connectivity fees the way if you were to deploy a like a cell phone backhaul or like a Starlink system to your stuff, which makes it like really kind of fun and super accessible for users. But this also raises a problem. If anyone who's walking nearby can connect and talk to whatever system or sensor that you've deployed, how do they know how to talk to that system and sensor that you've deployed? And this is where the LLM idea comes into play. So let's say I happen to deploy, for example, one of the demos. I'm here in DC. DC has a ton of air traffic. And so let's say I want to deploy on my network a aircraft monitoring node that will sit there, listen to ADS-B, log and save all the stats of the airplanes, what their ID is, where they're at, how high they are, how long they've been flying, et cetera, and let anyone who is nearby talk to that node and learn about what aircraft and helicopters are around them. Well, if I do it via a conventional way, I have to either periodically broadcast some message or like spam some link to a GitHub repo with a command list or some other thing to make it actually accessible to anyone on the network. This gets very old very quickly for everyone who is on the network daily and constantly dealing with these messages. And so I find personally a more better option is to do a technique that I call detraining. This is basically where you use an LLM as your middle layer. It is the interface between your end user or your human user and whatever system or sensor you've put on. And the job of that LLM is purely to act as a translation device and basically transform and translate whatever API architecture you have for your system into plain language that a human can understand and translate those plain language requests from the human into API calls for your system and sensor. It's a very basic transformer application, but that makes it really good for local models that normally can't handle a lot of complex tasks, and also makes it great in a Meshtastic environment because it means I don't need the user to have been on the network for so many days to have seen my spam. I also don't need the spam. So with that said, let's get into the first couple examples. So our first demo is going to be doing a ADSB spotter. This is going to consist of a Raspberry Pi that I have connected to over VNC. So you'll see the VNC screen up on my left or right, and you'll also see my phone screen on the other. This is because what is going to happen is the sensor is made up of a Raspberry Pi 5 16 gig. This is a little $10 Seed Studio LoRa radio, and this is a RTL SDR. I'm using a cheap 1 gigahertz antenna that's not technically correct for this, but he's listening to read ADSB, which is basically similar to dump 1090, listening for aircraft ADSB messages. Thankfully, I live literally right by DCA, so even though this is not an antenna setup I recommend for doing this if you were doing this for real, it should work and we'll be able to get things. So what will happen is, this is a Python script. This is called Plane Spotter in my Meshtastic demo repo, if you want to go and look at it. We have the model starts up, begin polling and broadcasting, and what will end up happening is we will see, oh, there it is. Plane Spotter is online and connected. So I have a private test channel called Z-Test, which is how the system, I can verify that like all my nodes are up and running and that they're working. This is a channel that's only seen by me and my node, so it doesn't actually spam the main chat. But if I go in and message Plane Spotter directly, I can now ask it questions like what does it see, how many aircraft there are, any specific details about the aircraft. So I will apologize, you'll see a bunch of old message traffic in there. That's from where I was testing stuff last night and earlier, but if I go and ask how many aircraft do you see right now? Yes, texting in front of a camera is that awkward. It will take roughly a minute for it to reply, but we should get a message from it soon. And so, okay, there it is on the, it's received the Meshtastic message now on the Pi. So you'll see in the VNC serial view, that is the user ID of my phone, which is technically using this Meshtastic radio to talk to it. And it will take about a minute to process and come up with an answer that should be 3 or 4. Right now, I'm not expecting to see a ton of aircraft, even though DCA is a very busy airport, but we should see several. So we're just going to wait and see. And while it's doing that, I will say this is a good example in a sense of ADS-B as a message structure is actually fairly complicated. It's not super confusing if you are an aircraft specialist, but the packet sizes are too much to actually dump on the network raw. They also are every quarter second. So if you wanted to do this sensor one way or the other, you would have to have some sort of collector and analyzer. And while it would be much faster to do it via an API, it is much easier for the user if they can just text it and get it. So there we've got 8 aircraft right now. And I can ask some basic questions like, are any of them, I don't think any of them are going to be on the ground. So I'll do, are any of them over 10,000 feet in altitude? One weird thing I will say on this, if you're not used to working in the aerospace industry, we don't make any sense because, well, everything is in meters, altitude is in feet. So I apologize for those of you, it is actually the correct nomenclature. Bear with me. I am also in the U.S., so we use imperial scale anyway, but for anyone who's wanting to do this in Europe and stuff like that, don't be surprised when everything is also in feet over there as far as altitudes, because that's the normal setup. But what is happening now is it's got my message. The model will be going in and pulling and checking all of the aircraft stats. ADS-B, which is the message structure we are listening to, basically is every half second the aircraft is broadcasting out its exact position, including its altitude and latitude, longitude, as well as any air and healthy safety stats. This is super nice because it means ATC operators don't have to personally manage every bird that is in the sky. Instead, they can do a lot of self-deconfliction between pilots and kind of monitor and get heads up of if and when something goes bad. But there are some complaints that the message traffic right now with how many aircraft we have gets a little too congested. And so there are currently a lot of efforts of making a next generation ADS-B, which will be a bit more dense in message structure, able to handle larger amounts of aircraft and everything else without constantly swarming all the channels. And I'm not quite sure why it's taking so long, but we'll just bear with it. The model we are using for this is Gemma 4, the Gemma 4 E2B, which is the smallest of the new Gemma models. It is designed, it's technically designed to run on Pis and everything else. It's really better if you run it on like a Jetson board as far as speed and efficiency. The Pi is a very bad device in this environment because since you're only really running everything on the CPU, you get CPU locked very, very quickly in this space. However, I find Raspberry Pis much more easier to set up and configure than NVIDIA Jetson boards. They are also much, much cheaper and much power efficient. And so, well, yes, you're not going to run either one of these off of a solar panel setup or anything like that. It is much easier to just have a Pi running outside on a wall outlet than necessarily a Jetson board. And there have been a lot of good work on making the Pis much more ruggedized and self-contained for that reason. So bear with me on the time. If you look through on the where I have the VNC view, what the Pi is seeing right now, you have the list of There's all the current aircraft it's tracking, their ADS-B codes, their altitudes. So you got one at 45,000 feet, one at 27,000 feet, one at looks like 40,000 feet and 32. So yeah, all of them are over 10,000. There it is. It just generated its reply, and we should see that on Meshtastic soon on the phone side. We are using in DC, we use long fast, which despite its name is actually one of the slower Meshtastic configurations. If you come to us in DEFCON, we'll be using short turbo, which is the fastest one and gets you like, I think like 10 or 20 kilobits per second, but at long fast for like 1 kilobit per second data rate. And there we go. It has shown up on the phone. Yes, for the planes currently tracked over 10,000 feet. And then there is their flight numbers as listed. So a little annoyed it didn't list the actual ADS-B calls instead, but that is the nature of doing this with an LLM. It's very it's a little non-deterministic in the output. This is just a demo of it. If you want to do this real, I would strongly recommend getting a little bit more robust on what you actually return as messaging, because the flight numbers aren't quite as useful as the ADS-B codes as far as a lookup. But it does answer the question, and it does give you that flexibility that we were talking about earlier. And so with that said, let's jump into another example. This one on a data link that you actually cannot do via conventional means over Meshtastic. Okay, so this is admittedly the silliest and least practical of the examples we're doing today, but I think it is funny and interesting and enough to worth coding in here. It's basically an open source flock camera that runs on Meshtastic. For those of you who might recall, I mentioned earlier that we can't actually do images and videos over Meshtastic because of data rate limits and bandwidth constraints. But if I use a local model to translate and basically transform a static picture into a text description, I can send that text description out over the network. And that's what we're doing here in this example. This is a demo called Trigger Camera in the Meshtastic demos. It works by some of the others. We have a Raspberry Pi 5. We have our LoRa module, same seed studio as the other two. But we also have a webcam. This is a cheap little $20 webcam. It's mainly just for the demo. And how this works is on the Raspberry Pi, in addition to the Gemma 4 E2B YOLO model, I also have running the Gemma E4 2B LLM model. I also have a YOLO model running. In this case, YOLO 26 from Ultralytics. And what happens is when I run the code, the camera will basically kick on, and the YOLO script will capture every frame from the camera and search for a object list that is controlled by the config helper in this project. In this case, I have it tagged to identify or to trigger on people, cars, trucks, and buses. So basically, think like if you put this like in a driveway camera or something like that to monitor who or what's going on in and out of the driveway, was kind of the joke idea that a friend of mine came up with. So that when that YOLO model triggers, it takes that image, it passes that to the LLM, and then generates a text description of that, which is pushed out on the network. So I'm going to go ahead and start the script now, and we can watch it run. So if I go ahead and I need to start recording first. Start recording, start running, start recording there. Now, trigger camera only sends messages to my test channel. It got a little bit too spy heavy to have it actually respond to any user's message for any object. Also, this thing takes like 5 to 10 minutes to respond. Local models do not process large context very well, especially on an edge device like a Pi where I am fully CPU locked. And so, whereas doing a normal pure text request, such as with the plane spotter or with my little Wi-Fi spotter, you can get a response within like a minute or two. Here, it's 5 to 10 minutes. It's very, very non-practical. So we'll probably do a cut in here while it's calculating. That way, you're not sitting here forever. But on the phone, we got our message saying it's live and what it's looking for. So if I take this camera now and I just point it at me, you get on the, you can see on the terminal window on the Pi that trigger detected, in this case for a person, because I am indeed a human. And now it will take the model several minutes to compute and cycle through. This would be much, much faster if you ran it on a cloud-based model, either by doing a purely cloud model like, Anthropic, OpenAI, or Google Gemini, or even if you had this like hooked up to a local network and you were running like a larger model on like a NVIDIA Spark board. This would probably be the best justification for doing a Jetson, because Jetson boards also have some GPU cores that would make this a lot faster. But I wanted to keep it easy and show that everything could be done on a Pi. And again, most of these are proof of concept demos meant to encourage you to build off of, and not like, hey, here, go do malicious stuff. Because, yeah, this is basically an open source flock camera. There's not a really better way to get around it and all of the spying problems that occurs in. And we're back. It actually took me a couple tries because the first time we missed the single Meshtastic package. Hence, while you'll see a slightly different setup on here on the outputs than when we started. But we did get a response. In this case, a man with full beard wearing a green shirt is facing the camera. The background shows some blue and white geometric patterns. I do not have a full beard currently, but I am wearing a green shirt and it is blue and white geometric patterns. And this one only took roughly 3 minutes to generate from whenever we prompted it. There were some earlier ones on there that did take longer. One took 5 minutes, one took 6 minutes. Again, this one is more of a joke version of it compared to the other two, but it does show that it can be possible, and it is something you could actually do usefully if you used more dedicated hardware for it. But that is it for trigger camera, and now we get to end with actually one of my favorite ones, Wi-Fi spotter. So we'll be right back. To finish things off, this is my favorite and in my opinion the most useful of the 3 demos we've gone over today. This is a Wi-Fi spotter, or possibly a drone spotter. I'll get into that in a second. This is a Raspberry Pi 16 gig, same as all the others. We are using a Panda Wi-Fi dongle that I'm putting into monitor mode to scan all of the valid network ranges that it can see and look at Wi-Fi beacons. And then we also have our little, our little Seed Studio LoRa board. This one is very nice and solves kind of a problem because similar to the plane spotter that we started with, where it's like, how do you do this complex data? This is, I feel, an actually like legit practical one that I actually do plan on deploying around the National Capital Region in a form where, in this case, the problem is when you're doing counter-UAS or counter-drone work, you are constantly forwarding and deploying a bunch of sensors, but then you also have to worry about, okay, how do I power or how do I do backhaul for those sensors like what is my network comp, and if you just use like an LTE modem, it gets kind of expensive fairly quickly on that, especially with all the plan management. Same thing with Starlinks. They're a little big and bulky for this stuff and are very power hungry. And so using Meshtastic and other LoRa networks looks super well in that space. The problem you run into then is the second half, which is how do I let everyone understand this? As we said, Meshtastic's a very slow network, as you've probably seen a couple of these. So I can't just live spam back regurgitating the hundreds of Wi-Fi beacon messages I will get anywhere in the National Capital Region. Because spoiler, we're a big city with a bunch of Wi-Fi networks, as well as a bunch of other stuff that talk. We are a very frequency dense community. So instead, what I'm doing here is I'm having the model track and analyze all of that, and you, Joe user, can talk to the system and ask it both in general, what is going on, how many channels are being seen, as well as more specific stuff, like asking for alerts if specific nodes work. And this matters because most Wi-Fi, most of your modern drones, I should say, like your cheap toy ones, all use a modified Wi-Fi chiplet. And so they all tend to have either the drone or the controller acting as like a Wi-Fi beacon slash hotspot that the other connects to, which makes them very cheap to see on hardware. This also makes them easy to spoof, but that's a whole other thing. But that makes something simple like this actually not half bad at seeing like roughly half the type of drones on the market. But with that said, I'm going to start the recordings now so that you can actually see this work. So there is the VNC running. There is my phone recording. So similar to the other ones, you will see in the phone view, it'll pop up soon that once it finishes doing its boot up and initialization, it will come online and send a message saying that the Wi-Fi dongle is ready to go. Yep, it's in monitor mode. Everything is looking good over there. And so now we should see the message on the spotter. Now the check-in thread has started. And then we'll go in and walk through some examples of how to use this. And hopefully you guys will like it as much as I do. So there we go. We just got our alert on the node saying it's running. So similar as before, I'm going to go in and I'm going to say, tell me how many networks you currently see. Now I'm in an apartment that has a hilariously bad Wi-Fi configuration, so there should be a lot that it reports back. Even though, again, this is a like $30 Panda dongle, so this doesn't have any custom antennas on it or anything like this. It's pretty much as simple as it gets. It will still pick up quite a bit. And so there, it got my message, it's processing it. So now it's going into the code and the model is going to be making a summary based off of each of the scan results that it's getting. So we'll just wait for that to get generated. And then we'll go from there. So. All right, so there it is. It generated the message, so now it's just going to send it over Meshtastic. Currently sees 70 networks. There it is. It's on the phone. Everything's fine and dandy. But as I said earlier, like you could also ask it, like, you know, what's on channel 11 or 13 or things like that, which is fine for if you're wanting to do like your own kind of wiggle Wi-Fi network or some other stuff. I care more about using it for getting alerts for whenever a network suddenly appears. So what I'm going to do is I'm going to, on the phone, basically ask it to set an alert the moment for if it sees any DJI drones. And this alert feature can be unique per user. So different clients can have different alerts, unlike the camera one where I was like, didn't want to consider that a little too creepy for what's meant to be a silly dumb project from a bet. This one is a bit more practical. You can send custom alerts for different accounts and stuff, which is nice if you're wanting to be alerted of like when a device gets within range or leaves range and things like that. Send me an alert if a DJI network is detected. And so I sent that message. It should get it soon. And once it does, and we've got the alert confirmation, I have on my desktop over here, I have a VM running another old project of mine called Naruto. Naruto is a drone spoofer. It's meant to basically spoof the Wi-Fi beacon messages common for a lot of these drones, like a lot of the old Parrot drones or your cheaper DJI drones all use this. And so it uses a similar Wi-Fi dongle to go in and generate basically fake Wi-Fi beacon messages, spoofing the SSID and the MAC address of those networks to make it appear as if it is a legit drone when it's not. And so we just got the alert confirmation on the VNC view. It just came over to my phone as well. Alert registered. You will be notified when a network matching DJI is seen. So now if I go in over here to, my apologies, I'm using the TV as a second monitor, and say okay, we should be, okay, I'm generating one DJI decoy on channel 3, and we should very quickly soon, within like a minute, it will hit the scan. Oh, there we go. It spotted it. Vendor DJI Technologies LLD. And there we go. We also got the alert on the phone saying that it recognized it. This is where I think it's super cool and where like Meshtastic really gets useful from like a sensor and system standpoint of being able to forward deploy to a bunch of nodes, not needing to worry about any of the management of those nodes, not needing to worry about are they on the same network, like have they all exchanged keys with each other, have they done all that jazz. You can just litter a field with them of all these scanners. They will just figure out how to talk to each other. They will figure out how to talk back to you. And if you do this kind of detraining of having a model on those sensors, or even at like a common endpoint for them, making it to where the human can now just talk to this network and get information back, I think is super cool. Like, I think this has a lot of potential and a lot of fun. As I said, I actually am talking with friends and we're planning to like try to deploy a more practical region for this. To help out with a problem a couple other old work colleagues are having. So maybe you'll see that if you're in the DC area. Who knows? But this kind of I think covers everything of like what I wanted to do. As I said, GitHub repo is below. You also probably came to this from the GitHub repo. If you have any other projects or ideas you would like to see done with Meshtastic in this space, let me know. Either leave a comment or leave a message on the GitHub repo and my GitHub repo, and I will try to, if it sounds fun, I'll try to do it by DEFCON and maybe have it shown live there, or I'll get around to it when I can. But thank you so much. Thank you for watching. Hope you enjoyed. See you in the next one.